My name is Tom Kantner. I'm a fourth-year aerospace engineering student, and this is my fourth year on UAS at UCLA. I'm the design and manufacturing team lead, where I oversee the integration and development of all the different subsystems with a focus on the mechanical subsystems. On the flight line, I will be on the assembly team and overseeing the mission success.
Hello, my name is Cameron Morshid. I am a third-year computer science electrical engineering student here at UCLA. My past experience with drones has been my internship at DJI this last summer and this coming summer. My role on a robotics and mechatronics laboratory here at UCLA called Romella, and my time on FIRST Robotics in high school. On the flight line, I will be the safety pilot for the competition and the controls oversight director.
My name is David Thorne. I'm a second-year aerospace engineering student. This is my second year with the team UAS at UCLA. I'm the airframe director. My primary projects have included the electronics box, antenna tracker, gimbal system, and airframe design. On the flight line, I'll be a part of the assembly team and in charge of pre-flight checks.
My name is Ryan Nemiroff. I'm a second-year computer engineering student, and this is my second year with UAS at UCLA. I lead the ground station development team, which develops software for managing communications and the AUVSI mission. I also worked on the electronics for the antenna tracker. On the flight line, I will help set up the ground station and manage the mission plan.
My name is Willie Teeve. I am a second-year aerospace engineering major. This is my second year being involved with UAS at UCLA. This year, I was on the airframe team, primarily working on the deployment system. On the flight line, I will be a general assembly team member and spotter.
Our UAS is a custom-built quadcopter with the primary airframe made of carbon fiber parts, which were custom manufactured by our team. The total wingspan of the vehicle is approximately 75 inches from propeller tip to tip, and it weighs in at approximately 35 pounds. Max thrust is approximately 80 to 100 pounds thrust. The ground vehicle used in this year's competition was 3D printed using PLA and optimized for minimal weight. Additional systems on the UAS include the gimbal system, electronics black box, battery pouch, and powertrain.
For manual flight, we use an RC controller which connects to an onboard RC receiver. Our ground station connects to the drone using both a 900 MHz radio signal and a 5 GHz Wi-Fi signal. The Wi-Fi link transmits data using Robot Operating System and interfaces with our custom ground station software for running real and simulated missions. The ground station connects to the UGV with a similar 433 MHz radio signal. We use a Pixhawk 1 flight controller with its built-in control software in addition to a Raspberry Pi 3 with our custom software to run our autonomous missions.
Controls on our drone is centered around the Pixhawk flight controller running alongside a Raspberry Pi companion computer. This setup has allowed our team to benefit from the stability of the community surrounding the Pixhawk hardware and PX4 software, while also having the flexibility to design custom control code for our drone. Low-level controls are handled by the PX4, including rate controller tuning and sensor estimation for flight. The Raspberry Pi performs position control by sending velocity commands to the Pixhawk, allowing fine control over the paths that the drone flies in order to effectively navigate around the obstacles and optimally reach rate points. Additionally, the Raspberry Pi controls all other actuators and indicators on the drone. Custom control software for the Pi synchronously sends signals to all components while the drone is in motion, allowing for precise control over where actuators are triggered and what alerts are triggered to notify the pilot about the status of the drone.
Our computer vision system is composed of three main components: the manual tagging interface, the database server, and the autonomous tagging pipeline. The manual tagging interface is integrated with the database and autonomous pipeline to highlight locations of possible objects to filter images of interest. The autonomous pipeline connects various image processing tools and convolutional neural networks to perform object detection, localization, and classification. This pipeline enables image processing to be reliably distributed across multiple computers and extended with additional functionality.
We plan on attempting to meet the timeline requirements with no needed timeouts. We're confident in our ability to do so because we have spent significant time optimizing weight and planning for ample battery storage. As of now, we are attempting fully autonomous flight, including takeoff, landing, and waypoint navigation without flying out of bounds. We have extensively tested and tuned our autonomous flight systems and have proven that we are capable of meeting the autonomous mission requirements. Our team will attempt obstacle avoidance and has spent the last year working on and improving our static obstacle avoidance algorithms. Given the results of testing, we believe that we will successfully be able to avoid these objects presented at competition.
We will attempt all object detection, classification, and localization. We are confident in our ability to complete these objectives because we have had 2 years of software development and a significant amount of synthetic testing. We will not attempt to autonomously detect the emergent object. Instead, our focus will be on standard object detection, including off-axis objects with some additional pre-processing to rectify the images. Our team will attempt to deploy our unmanned ground vehicle from the aerial system to the ground and also drive the UGV autonomously. At this time, we believe we will be able to deploy the system and are somewhat confident that we can make it to the final destination. UAS at UCLA is a team of dedicated, passionate engineers that have spent countless hours developing our system over the last 9 months. Our experience combined with our organizational pride will exemplify operational excellence throughout the competition, both to the judges and other competitors. UAS at UCLA utilized incremental testing spread over a span of time during the developmental process to save time, money, and resources while ensuring mission success. Many of the systems were first tested using simulations. Physical hardware was tested using finite element analysis to ensure that our structure could handle the appropriate loads and stress experienced during a typical mission. Controls and image recognition software was tested through custom flight scripts and computer-generated targets, respectively. Our custom ground station software, Flight Deck, also is utilized during simulation and allows for full stack development without using the drone hardware.
After simulation testing proved successful, prototype testing began on the individual subsystems. Autonomous control software was tested and debugged using smaller crash test drones with similar hardware at the flight field before being deployed to our actual competition flight system. Other subsystems, such as the UGV deployment mechanism, was first tested using prototype rigs and iterated upon before testing on the actual flight system. Once each subsystem was tested individually, they were placed on the flight system and tested together during actual mission scenarios at a local airfield. The results of these tests were examined and used to correct any errors that arose to guarantee mission success.
Up to this point, a majority of the flight time has been manual, as we have been spending most of our time tuning the aircraft and logging the required flight hours for the pilot safety log and proof of flight footage. As of now, our team has logged over 4 flight hours from this year over the course of 30 flights, with 3 hours being manual and 1 hour being autonomous. In order to tune our flight system, we utilized the built-in PX4 software in our PixHawk flight controller to generate logs showing responses of pitch, roll, and yaw, and other parameters to stimulus input. Using the results from these logs, we manually adjusted PID parameters to achieve the desired responses, verifying the manual and autonomous flight observations in real-world testing. Real-world waypoint accuracy was determined using a combination of visual indicators and flight logs from our PX4 flight controller system. Tuning parameters from our system have been extensively tested over the course of 60 quick takeoff landing flights, which have led to incremental changes to the PID and filter parameters used on our drone. Our team has also worked with the developers of the PX4 firmware to optimize the position hold accuracy of our system, which using their advice to reduce the amount of vibrations transmitted to the flight controller by the agricultural class motors used in our drone. Through automated testing of our control code, alongside a mock PX4 flight controller, our drone has hit over 1,000 waypoints while also applying our obstacle avoidance algorithm. In the real world, our drone has hit over 30 waypoints during mission tests, with an accuracy spread of under 2 meters. Data from these accuracy tests was collected using a modified version of Flight Review, which is PX4's log review tool, and also during visual verification at the field. Due to the nature of our flight platform being a drone, waypoint accuracy is expected to be very excellent at competition. Obstacle avoidance for this season used the rapidly exploring random trees algorithm for calculating a safe path around obstacles given by the interop system. Our obstacle avoidance code is built off a well-tested random trees algorithm using a linear transformation to map from field coordinates to a unit square. Testing of this algorithm was extensive, with over 1,000 obstacle and waypoint scenarios tested automatically by Jenkins, our continuous integration platform. Improvements to our obstacle avoidance algorithm, including an improved visual indicator on our ground station of the desired obstacle avoidance flight path, have also been refined and tested in simulation. In production, our obstacle avoidance algorithm has been tested in 3 full missions between this year's and last year's developmental cycles.
Our plan to ensure optimal image quality is to fix the shutter speed to the maximum of 1/4000th of a second and allow the camera to automatically adjust other parameters to compensate. Our camera was tested in different outdoor lighting conditions to account for different possible weather conditions at competition. Images of the same object were taken during a sunny day, a cloudy day, and at different times of the day, and later compared for consistency. The resolution of the images will be 5184 by 3456 pixels. Object detection and classification were primarily tested on synthetically generated sample images generated from background images of grass and images of targets overlaid on top. On 1,000 of these images, we were able to achieve 87% accuracy in shape detection and 90% accuracy in character detection. Localization performance was similarly tested on synthetically generated images. The accuracy was measured by the average distance from the ground truth bounding boxes. Our true positive rate was 80% and true negative rate was 93%. Airdrop testing was first performed in the lab using prototypes, then moved to the flight vehicle for airfield testing. Motor stall testing was performed to ensure it would be able to withstand the weight of the UGV. A rig with a nichrome wire was built to verify calculations for the current and voltage required to melt the fishing line. The motor was calibrated to test the lowering and release of the drone from lower heights off of the table, then moved to greater heights. Finally, the subsystem was placed on the flight vehicle and tested at the airfield in a real mission scenario.
As of this point, UAS at UCLA has attempted 5 on-site drops, with the payload surviving each time. The average distance from the target was approximately 10 feet. The UGV successfully arrived within 10 feet of the destination 3 out of 5 times. At this point, UAS at UCLA has completed 2 full mission tests, consisting of autonomous takeoff, waypoint navigation, image surveying, and landing. The deployment was tested separately outside the full mission test successfully, and the full mission test had the ground vehicle on board the UAS. We expect the deployment to integrate into the full mission successfully, and so only add a small artificial penalty for not including deployment in our full mission test. These full missions were tested at a local airfield using our custom flight deck ground station software to plan and execute the missions. During the first flight test, we found a bug in the open source PX4 firmware, which had a faulty fail-safe measure. We received a quick response from the developers, who were able to remove the faulty code and incorporate the change in their next release candidate. We also had issues with vibrations from the motors reaching the pixhawk, which led to us adding more vibration dampening measures. For our final test flight, we estimate a full score on timeline, full score on autonomous flight accomplished, 80% on waypoint capture and accuracy, 80% success on obstacle avoidance. We expect at least 60% success on image detection and classification, and a full score on the deployment section. Combined, we estimate our score on the final test to be approximately 85.6 points out of a possible 100 points.